Thank you, Mr. Schander, for the kind introduction, and good morning, ladies and gentlemen, and thank you for joining my presentation. My name is Tim Scheiden. I work as a research assistant at the Institute of Building Materials Science at the Leibniz University in Hanover. And now I would like to present you my presentation with the title Influence of Silica Fume on the Deterioration under Compressive Fatigue Loading in High-Strength Concrete. In the last decades, the focus in the research of concrete under fatigue loading was mainly set on the numbers of cycles to failure. Due to this, only little knowledge concerning the ongoing damage processes in the microstructure of concrete are available. Furthermore, it is known that the concrete composition and the resulting properties in the microstructure influence the mechanical behavior of concrete. Silica fume, for instance, leads to a strengthening of the cement stone matrix and the interfacial transition zone. This leads to an increase of the compressive strength under static compressive loading. But to which extent the silica fume improves or worsens the behavior under fatigue loading and how their ongoing damage mechanisms are characterized is not documented so far. Therefore, the main objective of this research is to examine the influence of silica fume in high-strength concrete under fatigue loading. Therefore, two concretes were investigated: one reference concrete without silica fume and one concrete composition with the silica fume. The storage and the testing conditions remain constant. With these concretes, the degradation mechanism based on damage indicators and damage parameters will be described. The considered damage indicators are based on the strain development and based on the acoustic emission. To investigate the influence of the silica fume, systematic tests with cylindrical specimen with a height of 180 millimeter and a diameter of 60 millimeter were obtained. Our specimen were stored in climate chamber conditions with constant temperature and relative humidity. The sinusoidal load frequency is set to 1 Hertz constant with a maximum stress level of 70 and 85%. Or 85% and a constant minimum stress level of 5% of the reference strength. In the first step, both concrete mixtures which differs in the addition of silica fume were characterized. So here we have the RH1B, the reference high-strength concrete without silica fume, which is the reference high-strength concrete in the priority program SPP 2020. And the concrete with silica, here yellow, which is a variation of the reference composition. As expected, the compressive strength increases, which is congruent with the literature, and also the modulus of elasticity also increases. The test setup is shown in the right picture with the different measurement equipment. In this research, the laser distance sensors were used for measuring the axial deformation, and the acoustic emission sensors were used for measuring the acoustic emission. The strain gauges and the LVDTs were used for investigations which are not part of this research. So let's come to the first results. For an overall classification of the results in the context, the numbers of cycles to failure are presented here in the slide. Marked in blue is the basalt concrete without silica fume, and in yellow, the concrete with silica. The results show that the addition of silica fume leads to higher numbers of cycles to failure. With decreasing stress level, this effect becomes more significant. We also can see that the scattering in the numbers of cycles to failure slightly increased due to the addition of the silica fume. But in general, we can say that the addition of silica fume leads to an increased fatigue behavior or increased fatigue resistance. The first selected damage indicator I want to present is the compressive strain. On the left side is shown the development of the compressive strain for the higher stress level of 85%, and on the right side, the one for 70%. In general, we see that both concretes on both stress levels have the typical S-shaped curves as we know from other investigations and from the literature. On both stress levels, it becomes clear that the concrete with silica fume has a higher initial strain which can be explained by the ratio of the applied stress in combination with the ratio of the modulus of elasticity. Also, the concrete with silica fume has a lower overall growth of strain due to the lower gradients, meaning lower strain increase per load cycle in the second phase and in the second phase. This behavior apply for both stress levels, meaning that the addition of silica fume leads generally to a lower strain development. The next image indicator is the stiffness, which is defined as a second modulus in the decreasing branch of the hysteresis loop. At the higher stress level on the left side, based on the gradients, it becomes clear that the addition of silica fume leads to a lower stiffness reduction per load cycle in the second phase. But due to the higher numbers of cycles to failure, the overall percentage stiffness reduction is similar to the concrete without silica fume. At the lower stress level on the right side, the behavior is reversed. Here, the stiffness reduction per load cycle in phase 2 is similar, but due to the higher numbers of cycles to failure, the overall percentage stiffness reduction is higher. Here it can be stated that the addition of silica fume leads to a different stiffness development with the dependency from the occurring stress levels. The next strain-dependent damage indicator is the dissipated energy as a measure for the viscous behavior, calculated as the area of the hysteresis loop in the stress-strain development for each load cycle. At the higher stress level on the left side, a lower initial dissipated energy and a lower energy dissipation per load cycle in phase 2, here in the middle, for the concrete with silica fume is recognizable. The same behavior can be observed on the right side at the lower stress level. But what is special here is the oscillating curves of the dissipated energy for the concrete with silica fume. We can see here this oscillating curves, meaning that the area of the hysteresis loop increases and decreases again within the second phase of the damage process. This leads to the assumption that temporal equilibrium states in the microstructure occurs, which are caused at the higher stress levels. In general, we can say that the silica fume reduces the displacement capability under fatigue loading. The last selected damage indicator I want to present is the acoustic emission, respectively the cumulated number of hits. One hit is therefore defined as a single transient signal recorded from one sensor. At the higher stress level on the left side, both concretes show a typical S-shaped curve similar to the strain development. But due to the addition of silica, absolute less hits over the fatigue process and less hits per cycle in phase 2, meaning a lower gradient, are detectable. Also, the transitions from phase 2 to phase 3, meaning these transitions here and here, correlates with the transition at the compressive strains. At the lower stress level, a stepwise curve is detectable for both concrete, which is more pronounced for the concrete with silica fume. Stepwise curves can be seen here, here, and here. Here it is recognizable that less hits in phase 2 up to the beginning of the stepwise curves for the concrete with silica fume are detectable, which is congruent with the higher stress level. So, but let's take a closer look at the lower stress level. Here we can see this stepwise curve as mentioned before. And the stepwise curve is an indication for a part of damage processes that occur in sections and on scales that are not directly detectable in the strain-dependent damage indicators, like the compressive strain. In the more horizontal parts, here, for example, or here, equilibrium states dominate in the microstructure so that less hits are detectable. In addition to the stepwise curves for the lower stress level, there's also a characteristic range of hits up to where an increased damage activity occurs. Here in blue is the range for the concrete without silica fume, here and here. And in yellow, the range for the concrete with silica fume. The ranges are also different for each concrete and furthermore stress independent, so that this range is for both stress levels. Okay, so let's come to a short summary. We have seen that the addition of silica fume leads to an increased compressive strength and modulus of elasticity. The fatigue resistance could generally improve by considering the numbers of cycles to failure. In addition, the addition of silica fume also leads to less acoustic emission hits under fatigue loading. Based on the acoustic emission, differences in the deterioration process between the stress levels could be shown, but becomes clear from the stepwise curves of the hits compared to the S-shaped curves. Furthermore, a concrete-specific range of hits could be detected up where an increased damage activity in the microstructure occurs. In the future research, detailed analysis of the acoustic emission hits using clustering methods are necessary to obtain more information about the characteristic of the hits to possibly assign them to a crack characteristic. Investigations of the microstructure with different imaging techniques concerning the damage development are still ongoing. Comparative analysis of the concretes with equivalent mortars to obtain the influence of the presence of coarse aggregates are also still ongoing. This also includes the analysis of the creep recovery behavior in order to evaluate individual damage components based on the strain development. Within the collaborative project of the priority program SPP 2020, the numerical model shall be extended with the gained knowledge. So I would like to thank you for your attention and would like to thank the German Research Foundation for the financial support. And for further information, feel free to contact me. And now I'm open for questions. Thank you.
Thank you very much, Tim, for the nice presentation. I noted for myself two questions, two short ones, which I would like to ask, and then I give the possibility to coaches or the audience.
Yeah.
Actually, these two questions were partially answered you by the Outlook section, but let's try to elaborate a bit more on that. So you claim in your paper that this effect can be explained by the addition of silica fume. I was wondering if you did or you plan to do further experiments concerning modifying the ratio of the silica fume or using other concrete recipients, other cement content and so on, so you can strengthen a bit this statement. This is the first question.
Is it right that you mean why we only change the content of silica fume?
Yeah, partially. And if you plan to do experiments with different amount of silica.
Yeah, the research objects, the research project, or in the research project, we change different properties of the microstructure with varying composition. So we change the coarse aggregate. We substitute the basalt of the reference concrete to a granite, which differs in the mechanical properties. We also change the water cement ratio for a weaker microstructure due to the higher water content, but only one property at one time, so that we can focus on one effect.
Okay.
Yeah.
Okay, so now I understand it better. Thank you.
Okay.
And the second question is related to your conclusion when you propose to do other test types, such as image technique, which you also mentioned here in the Outlook.
Yeah.
Did you do that? Can you elaborate a bit on that?
Yeah, we have microscopic analysis on thin sections for evaluating the damage in the microstructure. And we use fluence microscopy to have a better contrast between the single parts of the microstructure. Yeah.
Okay.
And we also use raster electron microscopy to have a better resolution. Yeah, to look further in the microstructure.
Okay. Okay. Thank you very much. This is all from my side. Now I would like to ask my colleagues if they have any questions or the audience.
Yes, thank you. I would like to have also 2 questions. I was very happy to see your results. I personally did a lot of tests with fatigue. I was happy to see this S type of curves in many times in your presentations, indicating differences with silica fume, so an improved fatigue behavior. I would like to have 2 special questions which needs a little bit thinking, and maybe it needs time, so I don't need a final answer. But it's interesting that I was developing now during your presentation. By applying, so we are speaking about fatigue. By applying silica fume and considering the type of deteriorations, deformations, modulus of elasticity, strength, and so on, can you imagine that you can advise, you can make an observation on increase of maximum strain in fatigue by applying silica fume compared to the normal concrete?
I didn't understand right. Can you repeat?
Yes. So the failure in fatigue is based on the strain behavior. So when failure is reached when a specific strain is reached. So not a stress is very important. So is there any chance to increase the maximum strain in case of fatigue by silica fume? Do you think it's possible? Did you have a measurement, any measurement? But I'm speaking about the maximum strain when the concrete fails.
Yeah. So the problem is, or not the problem, but the fact is that we have no limit criterion for a strain. So not a limit strain at which the concrete failures.
Yeah.
So the strain at failure for both concretes is different. So I don't know if the strain is the right indicator for the failure to predict the failure.
How do you predict the failure?
Yeah, if we could predict failure, it would be very, very good. I think to predict failure is in general not so easy.
Tim, the answer of my question is here. If you consider diagram, the left diagram, and you consider the top 2 blue and yellow curves, the maximum strain, this is compressive strain, almost at the same level, 3 microstrains. So the answer to my question could be that there is no influence. If we consider this diagram, it might be there is no influence, but if you go into details, and you can tell me next week, for example, so is there any increase of the points of the increasing deformation, so the vertical part, the blue lines and the yellow lines.
Mm-hmm.
If there is a 5 or 10% increase, this is interesting.
Yeah,
and
okay.
you can make one point of your PhD research a new point. Do you understand what I mean?
Yeah, I think so. And
this is very interesting. By the way, it seems to me that there is a little increase.
Okay.
So the other question is also some thinking. You were speaking about creep recovery.
Yeah.
Can we imagine better creep recovery by applying silica fume or not? So there is a way of thinking. There is no increase. You can develop a way of thinking with yes. What do you think about that?
Yeah, the creep recovery shall be differentiated in the different strain parts. What we have seen that we have less plastic deformations due to the addition of silica fume. So, but what's the definition of better creep recovery?
More intensive recovery.
So more elastic strains.
Yes.
So the first results showed that there's not more elastic strain in recovery due to the addition of silica. Yeah.
Yes, I also agree, because this is a kind of micro failure.
Yeah.
So there is no much difference for me. So I would not consider too much difference in creep recovery.
Yeah.
This is why I wanted to ask it. But very interesting research. So if you can come back to the first point next week,
yeah,
I would be happy to see that. Okay, yeah. Thank you.
Thank you.
So please.
I have one question if the time allows.
Mm-hmm.
Okay, so my question is about the acoustic emission that you used. I have actually, it has two parts. First is about the experimental setup. What kind of sensors that you used in your acoustic emission setup?
Here we use wideband sensors, 6 attached on the specimen, 3 in the lower third, and 3 in the higher third, with a distance of 60 degrees. So we have the full 360-degree. Yeah.
So they are all equally spaced and they are symmetrical in their arrangement. Okay, because if the cracking will not be symmetrical. So just to make sure that the sensors collectively they capture same kind of activity in different tests. So it's good to have
it's the same attachment for every test and test setup.
So my second part of the question is that you in your acoustic emission you basically use 2 parameters. First is the acoustic emission. First is the energy dissipation, and second is the hits. Just to make sure, I mean, just to know what is your interpretation about the energy dissipation. If there is more energy dissipation, is it that means less damage? Or does if you have higher energy dissipation, that means higher damage? So what is your interpretation for that?
Yeah, the dissipated energy shown here is the dissipated energy based on the hysteresis loops from the strain development. It's not based on the acoustic emission. From the acoustic emission, the results I shown here are only the number of acoustic emission, the hits. But only to say what kind of crack we have based on the energy is not possible in my opinion, because the energy is calculated as the area, and the area is influenced by the maximum peak level or the length of the hit. So there are more parameters to consider to take or to say something about the ongoing damage mechanism. So that was what I mentioned in the outlook, that we use clustering methods, which consider more characteristic of the hits to say something about the occurring damage.
So coming to the clustering method, so you going to use only hits to do the correct clustering, or will you use other parameters as well for clustering method?
I use parameters from the hits. So we use the rise time, the amplitude, and the frequency. And over these parameters, we can do a clustering, and yeah. So different characteristics from the occurring hits.
Okay, thank you.
Thank you.